I want to look for just a second at the formula for a two-proportion hypothesis test to see where that comes from. So first, I remember the general formula is that the test statistic equals the statistic minus the parameter over the standard deviation of the statistic. And so, for example, that could look something like this. Z equals p hat minus p over the square root of p times 1 minus p over n. And that looks great when I have a single sample proportion. But what if I want to determine if there is a difference between P1 and P2? I now have a two proportion problem, and I'm trying to estimate the difference in proportion 1 and proportion 2. Well, as it turns out, that test statistic is still a Z, but now my statistic is the difference in these two p hats. Before, it was just p hat. Now it's the difference in those p hats. The parameter then is the true difference, just like before it was p, now it's p1 minus p2. And then the bottom of this formula, the standard deviation of the statistic, is going to take me just a second. So I know with the first group, I've got this. But with the second group, I have this. And I've got to figure out how to combine those two standard deviations. So it takes us back to what we did a little bit ago, where we wanted to find the standard deviation of the difference of two random variables. In this case, now these are the proportions. Well, we discovered that we really didn't like to do that. What we wanted to do was find the variance of that, and then if we needed to find standard deviation, square root it. And as it turned out, the variance of x minus y was actually the same as the variance of x plus y. And if x and y were independent, then we could simply calculate this. And this idea of the two groups being independent is why that condition is important for what we're doing now. So if I consider first this, the variance of this side is what I had before, P1, 1 minus P1 over N1 with the square root, but then I still need to square it all. So I need this. And likewise, when I want to find the variance of that, it's exactly what I have written there. But again, it's squared. And then I'll add these two things together. Now what I find right there is actually the variance. And so if I want the standard deviation, then I need to take that whole thing and square root it. That looks really complicated, but as it turns out, a lot of it disappears. For example, I notice that, whoop, let's not do it that way, that this square root and that square cancel out. And likewise, this square root and that square cancel out. So I'm going to use my eraser and get rid of them. This is going to make this formula look a lot more palatable. Same thing over here. That square and that square root cancel out. Now I had deleted a little bit too much. So we can see this was P1, 1 minus P1. There we go. So that's what we're left with, and that's what goes on the bottom of this fraction right here, the square root of P1, 1 minus P1 over N1 plus P2, 1 minus P2 over N2. But alas, as I start plugging numbers in, I realize that I know what p hat 1 and p hat 2 are. Those are whatever numbers I got when I took my samples. The problem is I don't know what P1 and P2 actually are. I don't know the true values. Well, it turns out that this part right here is easily handled because my null hypothesis was that P1 equals P2, which means that P1 minus P2 must be 0. So this part of my formula disappears, and I don't really need that. On the bottom, however, I get in a little bit of a pickle. This stuff right here, I don't know. And so what do I have to do? Well, I have to use the next best thing. And so the next best thing is when I put hats on here and I use my guesses for P1 and P2. But as they say on late night infomercials, but wait, there's more. If I really want to have a good estimate for P1 and P2, I want to lump everybody together because under this condition, this hypothesis, there's no real difference in my two different samples. Proportion 1 and proportion 2 might as well all be lumped together. Let's say, for example, that proportion 1 was 17 out of 30, and proportion 2 was 13 out of 40. A better guess, if there really is no difference here, a better guess for the true proportion would be to say, in the whole group, how many people said yes? 30 of them. And in the whole group, how many people are there? 70. This is what we call the pooled p hat. The pooled p hat is a better guess for P1 and P2 than either P hat 1 or P hat 2 because I've taken a larger sample. And if it's random, that larger sample is something I'm more interested in using. So what does that mean? That means that in my original standard deviation formula, those subscripts by the p hats don't need to be there. So these subscripts can go away. I don't think that it's critical that you understand where this formula came from, but I do think that it's helpful if you can understand the background from what we just did. That's the formula that we want to use for a two proportion hypothesis test.